Hi, everybody.
With the all-new SuperSport Relive, we've reorganized our channels to bring you the very best documentaries, movies, and moments from all the sports you love. SuperSport 1 is coming to DSTV Compact with the best stories in all of sport. SuperSport 2 is a petrol head's dream. And 3 gives us the Invincibles, the Unthinkables, and all things English Premier League. Over on 4, it gets bigger and badder. SuperSport 5 is golf, while 6 serves you stories and slams. 7 is for the ultimate football fan.
Scored for Nigeria!
And it's all on DSTV Access. SuperSport 8 is a knockout blow. And 9 is an African celebration.
Celebration time for Green Eagles.
SuperSport 10 gives us more of the beautiful game. 11 is the home of cricket and rugby. And 12 is a gamer's paradise. Relive it all from Ali to Zidane and more with the new SuperSport Relive, bringing you the greatest stories in sport.
This broadcast is made possible by the Capricorn Group.
That we must have a look at is the coordinate bonds. Now I said to you, coordinate bonds are formed when one atom gives the shared electrons. The other one doesn't have any electrons. One of the examples was ammonia reacts with a proton to form ammonium plus. The positive charge lies on the whole molecule. You can't pinpoint it to a specific part on the molecule. All right. The other example of a coordinate bond was the H3O molecule. I showed that one to you as well. If we have water, it can react with a proton. It's the proton carrier in the acid base, and it forms as H3O plus, like that. And if I had to draw it to show you, then the oxygen lies there with the 2 hydrogens. Oxygen has got 2 lone pairs, and there we go. And when it forms this molecule, we have a hydrogen in the form of a proton attaching, and the whole molecule becomes positive. All right. But they are fairly simple. It's actually easy to see where the coordinate bond lies. Yes? Hydrogen gas is flammable, yes. Yes, then it's molecular. Yeah, this is then it's like this. Okay, this is an ion that goes into solution. Okay. Now, the third one that you need to know of how a coordinate bond is formed is with carbon monoxide, and this one isn't in your textbooks. All right? Now, carbon has got 4 electrons and oxygen has 6. So what happens is, if I have a carbon atom, or take that oxygen and that one carbon, the carbon having 4 electrons is going to bond by sharing one, sharing another, and then, no, I want to do it in black. The oxygen gives the 2 electrons, actually there like that. Oxygen's 1, 2, 3, 4, 5, 6. There we have carbon monoxide. No, the carbon. Oh, I've got it the wrong way around. The carbon. Let me start again. Carbon bonds onto oxygen. Carbon and oxygen. All right. The carbon has got 4 electrons. It's going to bond there and there. And there's the single pair of the carbons. Oxygen has got 6 electrons. 1, 2 form a bond like that. 3, 4, there's a coordinate bond. 5, 6. Sorry about the first one. Okay. So we can have a coordinate bond formed together with normal covalent bonds. All right. Are you with me? So they both have a single pair of electrons in the outer shell, and there is a triple bond holding the carbon onto the oxygen to form carbon monoxide. Yes. No? Yes? It gives a pair, but remember oxygen has how many outer shell electrons? 6. 1, 2, 3, 4, 5, 6. Yes, once they've been formed, once that bond is formed, you can't distinguish it from the others. All right, but that's to explain the formation of carbon monoxide. It's a coordinate, yes, it's also a bonding pair. All right, a coordinate bond in the carbon monoxide molecule. Okay. Yeah, you don't have to know them all. Say again? Then it's got a double bond and 4 electrons in the outer shell. You with me? Oxygen will do that. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yes, to make a triple bond to form carbon monoxide. Relatively, yes, it can burn further to form carbon dioxide. Yes, this stuff likes to attach because there's a lone pair with which it can attach on each side. And it attaches by means of a coordinate bond on the hemoglobin molecule. Yes. Do you understand? All right. Okay. They explain some of the polyatomic ions in your textbook. They're on page 34. All right. There they explain and they show you how H2SO4 is formed, figure 2.33. Just have a look at the structure. The sulfur is the center atom. Onto it bonds 4 oxygens. 2 of the oxygens are bonded with normal covalent bonds and 2 are bonded with coordinate bonds. Can you see that? The electrons coming from the sulfur. And then onto the oxygen molecules that bonded with a normal covalent bond, each one takes the hydrogen for the H2SO4. Can you see that? The sulfate is -2 because the hydrogens, okay. Then, that's the sulfuric acid one that they've got there, but that one is not specifically specified. The ones that I've done is what you must know the structure of. The next part, they discuss macromolecules. What is a macromolecule? Macro? Big. Normal molecules contain 1 or 2 or 3 atoms. Water is H2O, 3 atoms. Carbon dioxide is 3 atoms. Hydrogen sulfide is 3 atoms. They are just a few atoms together. When we have macromolecules, then we find that we get very large molecules with thousands of atoms in them. We get 2 types of macromolecules. The one is a polymer, and the other is a giant covalent structure. The definition of a polymer is a long chain-like molecule. Your hair is a polymer, long chain-like molecules. The cellulose fiber, yes, keratin is a polymer. The cellulose fiber in wood, it has a grain. Okay, if you can pull out one of them and you break a branch of a tree, it pulls off a thread. It's cellulose molecules. They are polymers, long chain-like molecules. When we make plastics, we make polymers. Long chains of carbons and hydrogens. And that is why plastic, if you tear it in one direction, it doesn't want to go, but in the other direction it does. It's got to do with the structure of the molecules and the forces holding them together. The giant covalent structures are, the examples we do are diamonds, graphite, and silicon dioxide. And each of them have their own unique structures. What makes diamonds exceptional is the fact, remember, carbon has got 4 bonding places. So when diamonds were formed, each carbon is bonded covalently in 3 dimensions onto 4 others. And each of those carbons in turn are bonded covalently onto 4 others, and it forms a network of covalent bonds holding the atoms together. One single carbon is held by 4 bonds in diamond, and that is why diamonds are so very hard, difficult to break. In graphite, we find that each carbon is bonded onto 3 others in ring-like structures. Okay, there we go. You can, yeah, you should be able to draw it like this. Whoops, no. Wait, yes, it's 1, 2, 3, 4. No. No, no, no. No, 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 no. Well, there we must go. There. I always draw it wrong. There. Okay. So each carbon is maximally bonded onto 3 others. So we have a single bond that is not bonded. Now, these ring-like structures form layers, almost like sheets of paper lying in a stack. All right? What forces do we have between molecules? Weak van der Waals forces. So in graphite, these layers can slide off each other. All right? That is why they use it as a lubricant. And why they use it in pencil lead, because when the friction from writing on the paper rubs off a layer of the graphite. But graphite will conduct electricity because it has a free electron that's not held in a bond. But if we go back to the structure of diamonds, where each carbon is bonded onto 4 others, are there any free electrons? Can diamonds conduct electricity? No. All right, so diamonds and graphites, we say they are different crystalline structures of the same element. We call them allotropes. Different crystalline structures for the same element. Diamonds and graphite. You need to know why diamond is strong. You need to know why diamonds do not conduct. You need to know why graphite is soft. And you need to know why graphites conduct. They ask this year after year after year after year. Yes. Some of the diamonds have impurities in them. And this is because in the sublimation process, it depends on what is in the trapped atmosphere. Lots of carbon under pressure, it undergoes like a sublimation or a deposition. And then if there is some sulfur or some whatever, metals, whatever, then they are sometimes trapped. And that is what makes one diamond more valuable than another. And that is why they also have different colors. You get yellow diamonds and blue diamonds. And all right, but that's got to do with the impurities that are in them. All right. Silicon dioxide, in your textbooks, we don't have it. Okay. We have that silicon bonds onto oxygen, and then it goes onto silicon and oxygen like that. Each silicon, if it looks, has two oxygens. All right. Forming a three-dimensional structure. Silicon dioxide, sand. Make glass from it. Okay? They don't ask too much on the silicon dioxide one for some other reason. There is another crystalline structure for carbon. It's less well known than diamonds and graphite. They call them Buckminster fullerene or just fullerene or buckyballs. And they are carbon atoms that bond in the shape like a soccer ball, the little patches on the soccer ball that are stitched together. That is what the fullerene look like. This one has got 60 carbons. From these fullerenes, they can produce tubes, and this is where the carbon fiber starts coming in when they make strong materials with carbon fiber. All right, it's playing around with the crystalline structure of the fullerene and the graphite that makes the sheets. They close it up in a tube, and then you get a very strong structure because it's covalently bonded. Okay, but it's very light because there's lots of air in between. The molecule is not solid. Metallic bonds. With metallic bonds, we basically do positive atomic rest surrounded by a sea of delocalized electrons. What are the properties of metals? Shiny, malleable, ductile, sonorous, good conductors of heat, good conductors of electricity. All right. The reason why they have these properties are due to the delocalized electrons. Metals are shiny because the electrons are reflected. The electrons on the surface of the metal reflect light. All right. They are sonorous because the electrons help carry the vibration of the sound through the metal, because the electrons that are delocalized are free to move. They are malleable and ductile, workable. You can hit it with a hammer or you can pull it into threads, because the positive atomic rests have the ability to slide over each other, and the negative delocalized electrons in between maintain the attractive forces. So it doesn't shatter like something else would have. Malleable, ductile, good conductors of heat and electricity. The delocalized electrons carry the charge. Conduction implies energy is transferred from particle to particle. We've done conduction, convection, and radiation. Okay? Metals are good conductors. Non-metals are poor conductors. Why?
Because there's not any delocalized.
Metals are better conductors than the other solids because the delocalized electrons can take the energy and carry it through the metal much faster than what it goes from particle to particle to particle. It does go like that in metals, but it also goes with the electrons, and that is why metals are much better conductors of heat and electricity than what? Non-metals are, because they don't have the delocalized electrons. I think I must stop there.
From Cape to Cairo, Accra to Antananarivo, there are millions of people just like you trying to make a living to make money. And there's no magic way to get rich quick, unless you're Aliko Dangote. You're not Aliko Dangote, are you? No? Well, perhaps we can help you get a little further along the way. With BBC reporters all over Africa, we find the stories, the successes, and the startups that will help you make the most of your money. This is Smart Money.
That we must do has got to do with writing balanced chemical equations. The heading in your textbooks there on page 38 is chemical shorthand. Now there's nothing new. If I, for example, have, let's have a neutralization, calcium hydroxide plus hydrochloric, I will get calcium chloride plus water. Now, we can go and add in something called state symbols. Calcium hydroxide is water soluble. Acids are also water soluble. Calcium chloride is also AQ. This was not such a good one. And water is a liquid.
So AQ stands as aquatic.
Aquatic, yes, water soluble. If I, for example, said calcium carbonate, this stuff is a solid, plus we can take hydrochloric acid, which is aqueous. There we go. And we will get calcium chloride, also aqueous, plus water, plus carbon dioxide. Technically, at this point, no. Okay. They usually will give an indication. You should know that copper sulfate dissolves in water. You know, the ones that we've worked with. Yes, yes. All right. So we refer to something known as state symbols. Now, the state symbols can indicate solid, liquid, or gas, and water soluble. All right.
So calcium carbonate, is that water soluble?
What? Calcium carbonate is not water soluble, it's a solid.
If you get something that is a solid but it's still water soluble, like
There.
so you just leave away the
It's aqueous.
but you leave away the F for being solid.
Yeah, because it's dissolved in water. All right. We have to balance this equation. When we balance with large numbers in front of the formula. Well, you have to have your formula correct, okay? Now, if we start balancing, 1 calcium, 1 carbon, 1 carbon. We have 3 oxygens. Here I have 1, 2, 3 oxygens. 1 hydrogen, 2. So I will probably need a 2, and now I have 2 chlorines, but I have 2 chlorines there. It is balanced. When you balance, you don't change the formula, you use large numbers in front, but we've done that from grade 8 already. Okay, so you shouldn't have problems with that. Are you doing accounting? I suggest you pack it away. Right. Now, the next part in your textbook is ionic equation.